Okay, so good afternoon, everyone. Today we have the pleasure to receive Professor Masao Sako from UPenn, and he's going to talk about the transient sky with the dark energy survey. Thanks for accepting the invitation. Please, you can start.
All right. Thank you for giving me this opportunity. I see a lot of familiar names on my screen. It's good to see you, or I can't see you, but good to be together. Okay, so I'm going to talk about the different kinds of transient science that we can do with the dark energy survey. I'm going to focus on two sort of big topics. The first half of my talk is going to be the supernova cosmology effort that we have in the dark energy survey. And then I'm going to switch gears after that and talk about other kinds of transients that we can study with the dark energy survey. In particular, I will focus on solar system science that we can actually do. Many of the stuff that I'm showing is work done by the supernova and the transient and moving object working groups. These are two distinct working groups within DES. Okay, so let's start with the interesting supernova cosmology stuff that we're currently doing with DES. So this is a picture of the different possible kinds of universes that you could have depending on the amount of stuff there is in the universe. So this figure shows along the x-axis, the horizontal axis, it shows you the size of the universe. It's compressed down to 2 dimensions, but obviously there's more. And the vertical axis is time. So it starts in the past with presumably a Big Bang. The universe expands, and the line shows you the present state of the universe. And depending on the relative amount of, say, dark matter in the universe can contract because of gravitational attraction. So that's the left-hand picture that I'm showing. If you look at the right hand, you can also have, if you don't have much dark matter at all, it's possible to have a universe that is just expanding at a constant speed. So you can see that those arrows are straight lines. It is possible for a universe, not our universe, but it is possible for a universe to have a constant speed. And if it's in between, you would have different kinds of deceleration depending on how much mass there is. So we obviously can't see the future, but we can see the past. So everything below the present line, you could, in principle, look at and study. So we can study the expansion rate history of the universe, and that tells you, in principle, the amount of dark matter. There are 2 distinct measurements that you need to make in order to study the expansion history. You need the x-axis, which is really the redshift at different epochs of the universe, and then the y-axis, it's time, but it can also be interpreted as distance. So depending on the relation between the distance and the redshift that you end up measuring, you have different possible scenarios for the expansion history of the universe. So just to give you a concrete example, if you focus on that, I don't have a pointer, so I can't point at things, but if you look at the 3 universes and the lowest slice on the bottom, closest to the Big Bang. Okay, so pretend that those universes are the same, or that universe at that particular epoch is the same size. Light from that part of the universe will reach us, and it'll reach us at the same redshift because the relative size of the current universe and the size back then, it was the same for the 3 different universes. But the universe on the right, that particular epoch is farther away from us. And that's because, compared to the one universe on the left, that universe had a slower deceleration rate. So that same size universe was further back in distance. So you can sort of see that by measuring the relation between redshift and distance, you are essentially studying the expansion history of the universe. And the way to do this, or one way to do this, is with supernovae, which are what we call not exactly standard candles, but they are standardizable candles. And this is just a cartoon picture of what we think this particular type of supernova is. It's a white dwarf supernova or a type 1a supernova. There are two scenarios on the left and the right. In either case, there is one or more white dwarfs, which is supported by a electron degeneracy pressure. Through some kind of mechanism, the mass of the white dwarf goes up, either through accretion from the companion star, like you see on the right, or through a binary merger by emitting gravitational waves on the left. If you have too much mass in a single white dwarf, it becomes unstable. The equation of state becomes relativistic, it becomes unstable, and then you suddenly ignite thermonuclearly, and then everything blows up and you emit a lot of light. This single explosion of about a 1.4 solar mass white dwarf can be 10 billion times more luminous than our sun. And so these things can be detected out to very, very large distances. So I'm going to the next slide. So this is a diagram. It's called the Hubble diagram that shows the two measurements that we make with supernova. So I'm not showing any measurements here, but I'm showing theoretical calculations of the different expansion histories of the universe depending on the cosmological parameters. And in the 1990s, astronomers were trying to measure the deceleration parameter. People thought that the universe is decelerating because there's mass, and mass would slow things down or bring things back together. So they were trying to measure this deceleration parameter, which tells you directly the relative amount of mass in the universe. And so you see this equation, Q naught equals omega m over 2. They were precisely trying to measure omega m. And of course, I think most of you here know that that deceleration parameter turned out to be negative, meaning the universe is accelerating. The lower left figure is a plot that was made by Perlmutter and Schmidt in 2003. If you see, look at the bottom panel of that Hubble diagram, you see that the points at the higher redshifts between z of 0.03 and 1, those points are on average slightly above the horizontal dotted line, which means that those the distances of those supernovae came out to be slightly farther away than compared to a universe which is expanding at a constant speed. So you can only interpret that as the universe going through some phase of acceleration between now and then. And so Saul and Brian and Adam Rees were awarded the Nobel Prize. Breakthrough of the year in 1998, which is actually, it was a long time ago. Kind of scary. Okay, so what the measurement showed is that the universe turned out to be none of those three, or not even in between the first one and the third one. It turned out to be the one on the right. The supernovae came out to be farther away than the universe, the third universe from the left. And you can interpret that as an accelerating universe. Acceleration, of course, can't be done by gravity as we know it. Anyone who learned Newtonian gravity or even general relativity know that gravity can only attract and not be repulsive, at least the gravity that I know. So there has to be something else that's causing the universe, that's pushing out the stuff in the universe. We don't actually know what it is. Maybe it's a thing in the vacuum. Maybe general relativity is not correct on large cosmological scales, or small acceleration. We don't really know. But the measurements do indicate that the universe is indeed accelerating, whatever the cause is. So the dark energy survey is one of the surveys that is ongoing now, is trying to shed some new light on the nature of dark energy. So we're trying to make the best measurement of the expansion history of the universe. It's a big camera, 3 square degree camera. It's called a dark energy camera, or DE-cam. 500 million pixels. It's been mounted on the 4-meter Blanco telescope, which is down in Chile, actually closer to where you guys are. For me, it's down. It has several filters, U, G, R, I, Z, and Y. And it's a survey that was awarded 512 nights on this telescope over a five-year period. We started observing on September 2013. It's going to go on until February of 2018. We are currently in year 4 of our 5-year data collecting survey. It's also a community instrument, which means that you can write a proposal and do observing on this using this camera if you want. Okay, just show you some pictures. The top left is the focal plane, which has 62 science CCDs. Each CCD is 2,000 by 4,000 pixels, and then there are a handful of focusing chips. You see some big lenses, big lens on the right. On the lower right is a single monolithic filter that we have. So our focal plane is about 70 centimeters in diameter. That's how big our single filter is. You also see the shutter, the filter exchanger on the top. And so this camera, the telescope is old. It was built in 40, 50 years ago. But the camera is new, and so we had to make some changes to the telescope to mount this massive camera at prime focus. So June of 2012, the cage was installed on the top end of the telescope. July 2012, the picture on the top right, that's $80 million of stuff hanging from a wire just before being installed. And then nothing broke. Everything was installed successfully. In August 2012 picture, you can see the focal plane on the top end of the telescope. And in September 2012, we actually started taking data on this. So 4 years ago, or 3 years ago, 4 years ago. So this is the actual first image, first official image that was taken on this camera. So each picture, each exposure gives you 3 square degrees worth of pixels, 500 million pixels. The size of the old camera that was installed on this telescope is shown on scale on the bottom. So this is a big camera. A typical exposure contains 50,000 galaxies, maybe 10 galaxy clusters, even 10 active supernovae, lots of asteroids. We also get images of satellites that are orbiting around the Earth. So this is a picture, again, of the focal plane. That streak you see from the middle to the top left is the trail left by a satellite that's orbiting around the Earth. We also get airplanes that look like this. This is an exposure that completely destroyed our supernova observations. Okay. We even have non-detections of supernovae. The picture on the left is a decant picture taken on September 12th in 2012. There was a supernova that went off later in October 27th of that same year. And on the right, you see the picture on November 24th. The picture on the right is not a picture that we took, that someone else took. And you see that bright dot where you see those 2 orthogonal lines. That's the new supernova explosion that we didn't detect. So we even have non-detections, which is sometimes useful. Okay, so a little bit more about the survey, because it'll be important for not just for this half of the talk, but the second half as well. So we have a multi-tiered survey. The wide survey is a 5,000 square degree survey where we take 1.5 minute to 45-second exposures in G, R, I, Z, and Y. And you can see the footprint on the bottom. It looks like a to me it looks like an elephant with a gun on the head, but other people have different ways of picturing that. So 5,000 square degrees. In each of the 5 filters, we take 5 exposures, 5 visits. So any given spot on the sky within the footprint is observed 50 times in one of the 5 filters. Currently we have about 40,000 exposures that we've taken in that 5,000 square degrees. We have multiple exposures of the entire footprint by now, but not to the full depth. So that's the wide survey. The supernova survey has two different levels of depth, the shallow and the deep. The shallow consists of 8 DE cam pointings, and you can see them as little circles in the footprint. There are 10 circles total. 8 of them are shallow. We take exposures in GRIZ with exposure times listed there. It's 2 to 6 minutes, depending on the filter. But we visit these 8 fields once every 5 or 6 nights. And then we look for new transient objects that were not there, for example, the year before or earlier. So this is where we find our new supernova candidates. The deep field, there are 2 pointings. So 2 of the 10 circles are deep. We take much longer exposures, about a factor of 8 to 10 longer exposure, depending on the filter. So the shallow fields give you, on average, supernovae at around a redshift of 0.4, 0.5. The deep fields give you type 1a supernovae on average at around Z of 0.7, 0.8. But it goes up to about redshift 1.2. So it gives us a range of redshifts for supernovae that we can study. This is a nice movie. I don't know if it's showing up on your screen. It's a time sequence of the exposures that we took on our camera. I don't know if you can see it. But anyways, on the right is the date.
I can see it.
And then you can you see it?
Yeah.
Yeah, okay, good. So this is how we take exposures. And I've shown the exposures that we took from the first 3 years of our observations. Let me do it again. First year we focused along the equator and in the south. And then there's a break, and then second year we fill in the in-between, but also do some in the south. And then, so that's the end of the second year, and then third year we're filling in more holes and going deeper across the entire footprint. And then years 4 and 5 we'll go deeper everywhere within this footprint. Okay, so a little bit more about the supernova survey. So if you take those 8 shallow fields and 2 deep fields that make up about 30 square degrees on the sky, and you study that for 6 months every year for 5 years, you end up with about 2,500 really high-quality type 1a supernova light curves between a redshift of 0.2 and 1.2. The mean cadence is, so we're aiming for 5, but it's more like 7 because the weather has not been very good. And then one of our main goals is to get good I-band and Z-band light curves at redshift greater than about 0.9. This was not done previously by other surveys. The Supernova Legacy Survey, for example, is the previous deep supernova survey, went out to redshift of 0.9, 1, and 1.1, but they don't have good I-band and Z-band light curves. They have maybe one of them, I-band, but not Z-band. So you can't really measure colors with the with the SNLS data. We do real-time searching using difference imaging. So we take a picture one night, you subtract it, and then you look for things. I'll say a few more things about that. We can't get a spectrum of every type 1a supernova that we find. 2,500 1As over 5 years out to redshift 1 would require dedicated 10-meter telescopes, which we don't have. So what we do is we take a spectrum of a subset of our good type 1a sample, but then afterwards go back and get the spectrum of all of the host galaxies of the supernova candidates. So we have a dot in the sky, which we think is a supernova. We go back a year or more later and get the spectrum of the host galaxy, the nearest host galaxy. We actually take not just the nearest, but the few nearest galaxies. So we will at least have the redshift measured for most of those supernova candidates, although those redshifts could be wrong if the host galaxy has nothing to do with the actual supernova explosion. A little bit about difference imaging. So this is, so I have two pictures here, two pictures from the same piece of the sky. If you want to look for transient objects, say in the picture on the top, what you can do is take the picture on the bottom and literally subtract pixel by pixel. There's a lot of stuff you have to do before, like aligning the pixels, matching the PSF, and all that. But once you do that, you can literally subtract pixel by pixel. Without doing subtractions, it's hard to find new things that were not there before. So just by looking at this picture by eye, you won't be able to find anything. So this one picture is a single CCD, DCAM CCD, 4K by 2K. So this picture will fill up your entire 4K monitor if you have one. And we have 62 of these pictures per exposure, and we have 40,000 exposures. So you definitely don't want to do this by eye. So I'm going to take that little piece over there and then zoom in. You can see that there's a dot on the top, but not a dot on the bottom. If you take the top one and subtract the bottom one, you can see that most other things are subtracted nicely, but not perfectly, but most of the things are gone, and then the thing that is not in the template image appears in the difference image. You can see some leftover missubtractions of the stars, and this is something that's something that you have to live with unless you have really good astrometric solution in your images. Okay, so when we look for sources in the difference images, we get a lot of them because there are a lot of missubtractions. But most of them are junk image artifacts for subtractions, diffraction spikes, and so forth. And a graduate student at UC Berkeley has saved us and written a nice machine learning code that takes each of the detections, the images, the stamps that you see on the top left, and wrote a machine learning code that tells you, is it a good astronomical transient or is it not? And it has a really good performance. The graph on the left shows you on the y-axis the false positive rate, and the x-axis the missed detection rate. So if you look at that square that says 0.5, if we cut on a machine learning score at 0.5, you will have a missed detection of about 4% and a false positive rate of about 2.5%. So this was fantastic. We went down from literally tens of thousands of detections per night down to a few dozen. Okay, just another pretty picture. So this is 3 of our supernova fields that are next to each other in the Chandra Deep Field South, C1, C2, and C3. So this is about 9 square degrees and 1.5 billion pixels compared to the picture of the moon. This is a lot of data. I'll show you a few more cool pictures of some of the supernova candidates that we found. So again, this is 62 CCDs on DCAM. I'm going to zoom into one of the CCDs down there. And on the bottom is a spiral galaxy right there. This is picture taken one night. Some nights later, you see a dot. This was a type 1c supernova, so not one that is useful for cosmology, but nevertheless a good supernova at a redshift of 0.06. These are some example light curves. So it shows you the light curve quality from our data. The left panel shows a redshift of about 0.8 to 0.9 type 1a supernova light curves. On the right top is a low redshift one, or what we consider low, which is redshift 0.3, 0.4, really good light curves. And the bottom right is a higher redshift one, redshift of 0.9. This was a supernova that exploded 7 billion years ago when the universe was roughly half the current size, and the light is just reaching us. Puts things into perspective. Okay, some more nice pictures. This is again one chip on our camera. I'll show you a high redshift candidate. So zoom in there. There's that little fuzzy red galaxy in the middle. Doesn't look like much, but if you subtract the template, you end up with a detection that is many sigmas about noise. Right there. Okay. So what are we trying to do? Well, we're trying to measure the best expansion history measurement that was ever made. Before DES started, this was the state of the art. On the right is what's called the JLA sample, the Joint Light Curve Analysis sample, which consists primarily of intermediate redshift type 1As found by SDSS and high redshift type 1As found by the Supernova Legacy Survey and just a few from the HST survey. And then in blue shown here are the low redshift type 1A that are found in many other surveys. So on this diagram is 740 good, high-quality 1A distance measurements. And this was the state of the art, or I guess this is still the state of the art, published by Mark Betul in 2014. But we made a big progress from 2003, which is the picture, the Nobel Prize-winning picture, to the right. We're really making accurate and precise distance measurements as a function of redshift. And these are the constraints that won the Nobel Prize on the left, and then the JLA sample on the right. So the JLA constraints on the right, the x-axis is the matter density, the y-axis is dark energy density, and on the left, that red box corresponds to the figure on the right. So on the left, you can see that the contours fill pretty much that entire box, but we've made the contours substantially smaller with bigger samples and better, well-measured light curves. And these are the cosmological constraints that you get from the JLA sample. Sorry, this is the constraints on the evolution of dark energy that you get from the JLA sample. So W naught is the current equation of state, ratio of pressure and density. WA is a parameter that it just parameterizes any change in redshift. So when if WA is 0, then dark energy properties does not change with time, and that is consistent with our current measurements. What DES Supernova Survey will do is to make that next leap in decreasing the contours. So the top left again is the constraint on W naught and WA with the JLA sample, and on the top right is the constraint that we expect from the end of the DES survey by combining our data with SDSS, the redshift range that we don't quite get with DS, and the low redshift, which is another redshift range that we don't get with DS. But we are hoping to get these kinds of constraints. The area of the contours would be about a factor of 10 or more smaller than what it was before. So that's our hope. Any questions up until this point?
So how many supernovae did you observe so far?
So far we have spectra of a confirmation of about 400, not just type 1As, but mostly type 1As, but also other types, so 400 spectra total. We found about 1,500 so far, candidates, type 1A candidates, and got host galaxy redshifts for about 800 of them so far.
Okay, thanks. And When you're planning a release, you have...
So we're still, we haven't analyzed the light curves yet. We don't have the final light curves yet, so we're working on that. But we are working on a publication of the first 3-year data set, which is not even close to being done.
Okay.
So it'll be at least a couple of years.
Okay, thanks.
Yep.
Masao?
Yes.
You mentioned that the astrometry is bad, so that's because the exposure are so deep that the stars are saturated, right? Do you expect that Gaia will improve that for you?
Yeah, so the main problem, so the problem is it could be fixed now, but when we were running things, last year and the year before, the only catalog we had in that the southern sky was either USNO-B or 2MASS. And, they're good, but they're not good enough to give clean subtractions. And so you end up having those slightly misaligned stars that give those missed subtractions. But yes, you're right. Now that we have Gaia, we could go back, if we want to, in principle, and align the images more nicely and get cleaner subtractions. But we haven't done that yet.
Okay, thanks.
Okay. All right. So I'm going to move on to the second half of my talk and talk about other transients that we can study with DECam. So the supernova survey is great for studying things that rapidly change with time. So remember, our cadence is about 7 days. So if you have things that that vary on timescales of 7 days or longer, you could study with the supernova survey. However, the supernova survey is only 30 square degrees big. So what we decided to do was to try to look for transients, not just in the supernova survey, but in the 5,000 square degree wide survey. And there, you can't really study the time evolution of any particular object because we only take 50 pictures over a 5-year period. So if it changes rapidly, then we won't really be able to do anything with it. If it changes too slowly, maybe if it changes very slowly, you can study it. But it's not a well-controlled cadence, so it's very unpredictable. However, there are interesting solar system studies that you can do in the 5,000 square degree wide survey. So I'm going to focus on the solar system science that we've been doing. We have been doing these other things that are shown in this picture. We have followed up gravitational wave detections from LIGO, and there are papers that we published on that. We are also finding these things called tidal disruption events, which are events that happen when a star comes close to a supermassive black hole at the center of the galaxy. The tidal forces strip the star apart and produces very distinct signatures. I won't say anything about that. We can also study peculiar explosions if you sample a much larger area, if you study a much larger area in the sky. I won't say anything about that, but those are things that could be studied in a 5,000 square degree variability survey. So the 5,000 square degree wide survey, even though it doesn't have a well-controlled cadence, you could look for solar system objects which move across the sky. Just a few things about the things in our solar system and the stuff that we're focusing on right now. So this picture shows the inner solar system on the top left and moving out to the right and bottom, outer solar system and the Oort cloud and so forth. Studying certain kinds of objects in the solar system tell us about the formation and also the dynamical history of the solar system. In particular, the objects that are well outside the orbit of Neptune, which is the last big planet in our solar system, not counting Pluto, those things that are way out there, if they have perihelion distances that are much bigger than the Neptune's distance, which is 30 AU from the sun. Those objects are not interacting with the inner planets at all. And so by studying them, it's kind of like studying the what the solar system was doing 4.5 billion years ago. It's like a cold storage place that you can study, and you can learn about the solar system. So a lot of work has been going on currently, and there was some interesting stuff that came out early this year, where people studied. They looked at the objects that never come close to Neptune, and you can see that picture on the right. Those elliptical orbits, 1, 2, 3, 4, 5, 6 of them. They don't come close to Neptune, so they don't interact with Neptune, and so they're very stable and happily orbiting around the sun out there. And there are 6 of them, two of which were found by the dark energy camera. And people noticed some interesting patterns of these objects. So I'll come back to this point in a bit. But there are interesting things that you can study by looking at those very distant objects in the solar system. That region is called the Kuiper Belt. So Pluto is the first Kuiper Belt object that was found, even though it was originally a planet. Now it's a Kuiper Belt object found in 1930. The second Kuiper Belt object was found in 1992. It took 60 years to find that second one. And this is these are the pictures that were taken to discover this object. This object has a name of 1992 QB1. So what you do is you take a sequence of pictures separated by minutes, maybe hours, and solar system objects move across the sky. They move across the sky because of 2 reasons. Primarily because we're moving around the sun. And so you look at it one time, an object is there. The next time you look at it, the Earth is in a slightly different position, and parallax gives you a proper motion of the object. Also, the object is moving because presumably it's in a Keplerian orbit and moving around the sun. So you have a combination of our motion, the Earth's motion, and the object's motion that give rise to proper motion in the sky. So these 4 pictures, these were taken by Jewett and Liu, published in 1993. They surveyed a very small area in the sky, 0.7 square degrees down to about 25th magnitude, and try to look for these things. The 4 pictures here are separated by minutes to hours. You can see that object in the circle is moving across the sky. Slow-moving objects are farther away than nearby objects which move fast. So you see those streaks with arrows pointing to them. Those are main belt asteroids. They actually move during an exposure, so they leave a streak rather than a dot. Whereas the distant things like the Kuiper Belt objects mostly produce a point in an image. But if you take images back to back separated by minutes to hours, you can find its motion, or you can look for its motion. So this is the kind of thing that we're trying to do with the dark energy survey wide survey data. Another example here, this is an object that was found by DCAM, but not by the DES collaboration. There were community observers who took pictures just a few days after we've commissioned the telescope and found this object, 2012 VP113, which is one of the objects that I'll come back to later. The motion is very small because it's very distant. This one actually has the largest perihelion distance of all the known solar system objects. The closest it comes to Sun is 80 AU. Its aphelion distance is 450 AU. And again, these objects are completely detached from the inner major planets, and so they don't interact with those planets at all. You can study them. You can study its properties and learn about the dynamical history of the solar system. Okay, so there are several thousand Kuiper Belt objects. Another name for Kuiper Belt objects is trans-Neptunian objects, or TNOs. And there are many that are known, and this is a nice movie that Dave Gerdes made of the known trans-Neptunian objects and how they move across the sky as a function of time over a 5-year period. So every time an object does a loop, that corresponds to a year of observations. And so you can see these things that are circling around because of our motion around the sun, but they're also drifting, and that's due to their motion around the sun. So there are, quite a few known TNOs inside the DES footprint. And you can even see that some of them go through the supernova fields, which are have the dark circles. And we have rediscovered them in our data. But we're trying to do this more systematically. This is, again, 3 of the supernova fields. I think these are the X fields, 1 deep and 2 shallow fields. And the red dots corresponds to the actual observations and detections that we've made of, let's see, I think there are about a dozen TNOs shown in this. So by studying how it moves, you can measure its semi-major axis, eccentricity, inclination, and other angles that determine the orbit of the objects. We even found what's called Trojans, Jupiter Trojans. So Trojans, as I think many of you know, are objects that lie on a corner of an equal lateral triangle made by the Sun and Jupiter. So this is a movie of the Sun in the middle, and it's rotating with Jupiter that's on the right. And then the things that you see sort of swarming around the middle bottom of the Sun and Jupiter, these are the Trojans. This is a stable Lagrange point. If you put an object there, it'll wander around that point. And so in actually one single observation that we made with DCAM, we found 20 of them. And it took 65 years to find the first 20. So we've doubled this sample just in one night. So this was kind of interesting. We also found, this was a recent discovery, we ran our difference imaging pipeline on the, not all of the 5,000 square degree wide survey data, but about half of them. And we were looking for Planet 9, which I'll get to in a little bit. But we found this interesting or cool distant dwarf planet. This is one picture taken on 2012. October 21st. That arrow over there, you see that little dot. 2 days later, it's there. And then another few days later, it's there. So this is an object that is, by solar system standards, very slowly moving. It has a motion, proper motion of about a little over 1 arcsecond per hour. So in a week, it only moves, not even an entire CCD. So this is consistent with, with an object that has a semi-major axis of 109 astronomical units, perihelion distance of 38 AU, aphelion of 180 AU, has an orbital period of over 1,000 years. The current distance is 92 AU, and we were able to find it. I think it's the second most distant solar system object found during discovery. So 92 AU, I think, is the second farthest that we've seen in our solar system. So on the top right is the orbit of this new dwarf planet that we found. It has not a catchy name, 2014 UZ224. And you can see that orbit in comparison to Neptune. So it does come a little close to Neptune, but we've determined that the orbit of this dwarf planet is stable. It's not affected by Neptune. So DCAM data alone only give you reflected sunlight. So that information alone cannot be used to determine the size of the object. because it could either be a shiny small thing or a dull big thing. So it can't be used to measure the size of the object. But we got some data from ALMA. We put in a director's discretionary time proposal. The director accepted it. We have radio observations from ALMA that give us the intrinsic thermal emission from this object. So these things out there beyond Pluto have surface temperatures of 25 to 30 Kelvin, and ALMA is the place that that you can look at to detect the thermal emission. So we have the data in hand, and we're doing the size measurements right now. On the bottom figure shows you the actual track of this object. So it wasn't just detected in those 3 nights that I showed earlier. It was detected in close to a dozen nights. And the orbit of this thing nicely fits with the Keplerian orbit with parameters shown above. Okay, so this was found in our search for Planet 9. So Planet 9 is this thing that a hypothetical massive planet that was invented to explain this weird clustering of these 6 detached Kuiper belt objects that you see on the top right. Those 6 objects, you can see that the elliptical orbits are kind of aligned. Actually, the plane of the orbits are also kind of aligned. And that's shown in the 3 panels on the bottom. These are weird solar system people angles. But you can basically think of these 3 figures as the 3 Euler angles of the orbits of the 6 things. And they're all clustered. You can see those points on the left. The omega angle is all clustered around 90 degrees. The capital omega angle in the middle is clustered a little above 90 degrees. And the other angle, another omega, is clustered around 300 degrees, a little higher than 300 degrees. So these objects have weird, strange clustering in their orbital parameters. And Batygin and Brown earlier this year hypothesized that, well, if this isn't a chance coincidence, but if there is a dynamical explanation of this clustering, it can be explained by this hypothetical massive planet that has a really large semi-major axis, somewhere between 200 to maybe 1,000 astronomical units, and has a mass of about 10 times the mass of the Earth. the Earth. So they called this hypothetical planet Planet 9 I guess to mean that this would be the real Planet 9 if it exists. And that dashed orbit is is one example of what Planet 9 could have in its orbit relative to the 6 Kuiper belt objects that are known. So we are searching for this thing. They have dynamical models give you roughly which orbits would be consistent with these 6 clustering of these 6 Kuiper belt objects. Those are shown on the left of this figure. But it's a big swath in the sky, and you don't really know where it is. So if you overlay their prediction on on this picture, which is the full sky, overlaid has our DES footprint, and this is not a very scientific figure, but the black lines, which are their different models for Planet 9, parts of it go through our footprint. So we are looking for this thing in our data currently. I guess I could tell you that we haven't found it, or I'm not telling you that we haven't found it. But we are searching. We're still analyzing the data. We haven't looked at all the data yet. But it's also possible to look for this thing not just in the dark energy survey data, but in all of the data that were taken using DCAM. So DCAM is a community instrument. It's been used by many people around the world. This picture shows all the exposures that were taken in the R band by DCAM as of a little earlier this year. So we could, in principle, search in that data as well. Okay, so I'm going to stop there and take questions. Thank you.
Okay, thank you very much. We have time for questions.
Questions?
Questions?
Masao?
Okay.
Yes.
Masao. So
Yes.
I think it's only DS people left here. So
Oh, okay.
uh, what's going on with this discussion about the different stacking of the default data? Let me rephrase that. So the supernova working group had a paper, Bursting et al., I don't know, 2012 maybe, about the simulating predictions for DS, right?
Yes.
And a magnitude limit of 27 or so in G-band and
Yes.
and 28 after 5 years. So have you checked how this compared the simulations previous to the Dark Energy survey, and how we are doing in terms of depth?
So why the numbers went down?
Well, so yeah, the numbers went down, right?
Yeah.
And so there's all this discussion about cleaning the stacks and getting just what's best, and how this could affect you, or it doesn't affect.
So there's a difference between the predictions in the Bernstein paper and the actual data. The actual data are much worse than what we thought the data would be. So for example, to be specific, we used a seeing distribution in our simulations, which was much better than what we're currently getting. The seeing, on average, we were hoping to be around 1.1 arcsecond, but it's much worse. We're getting much worse than that. So that gives us a hit in the magnitude limit of about 0.2 to 0.3 magnitudes, and so we're shallower than our predictions.
Yeah, it's been unexpected weather, right?
Yeah, the weather. Yeah, weather, and so I think that seeing distribution that we assumed was predicted seeing at zenith, which we didn't know. The actual PSF, we slew the telescope down closer to the horizon, and the seeing is worse. So, yeah, it's worse conditions, and the cadence is worse than our simulations. Yeah, so that's the main difference. But we understand the difference now.
Okay. Do you have a sense of how deep you will get in year 3?
So year 3 was last year. It was horrible. It was the worst weather since Blanco was built. This year is slightly better. So the 2500 that I showed is the predicted number based on the first 3 years of data.
Okay.
I have a question. There's a recent paper stating that the confidence we have in accelerations actually is smaller than we thought. So what's your opinion on that?
Yes, I haven't read that paper carefully. I've only heard people around me talk about it. So I don't know the details, but people tell me that they made about 10 different mistakes in that paper. So I don't. So for example, if you look at our data, there's no doubt that there is acceleration. So whatever they're doing is not right, or not the same as what, for example, the JLA people did.
Okay, thanks. More questions?
So about this particular, this was a scientific report, right? There is some saying also that the media was too loud about the results, that the results are not that bad. Then they just said, oh, dark energy doesn't exist, and they
Yeah,
they
and
overstretched the
they
conclusions.
didn't use priors that they should have used, and yeah, the media really amplified it.
Yeah, it almost like a, okay, I won't say it.
Yeah.
Okay, so there are no more questions, so let's thank our speaker again. And so very nice to have you here. And thanks everybody for attending, and see you all soon.
Thank you.
Masao, bye.